So that brings me to the second AI, Erica, which looks at one still image, not time-lapse. You can use time-lapse if you want to, but just looks at one still image, because most programs in the world use still images to look at embryos and evaluate the data. So it's easy on any microscope setup to make a still image. It's more complicated and more expensive to do time-lapse. So we chose for this option first. And then it looks at this particular AI, looks at the highest ranking and was trained on euploidy assessment. There are now several other AIs that do the same and were trained in the same way, but this was the first one that did this. And if we look at the first version that was developed, again, here we have a second version now, feed 2.1.2.0. The first version was relatively slow. Embryologists complained how long it would take. Basically, you take pictures and then you drop them on the screen in an interface, and then the computer, the system, remotely would calculate how it would rank the embryos. It would take 3 minutes. Now that is a few seconds. So that's one big improvement that there have been. It's a different algorithm that was developed. The first one was developed on 1,200 embryos and only could distinguish between aneuploid and euploid. Now it also can distinguish between mosaicism and aneuploid and euploid, and was used on 7,000 embryos. But the big difference is the first data set was on 1 clinic, the second data set is on 42 clinics. So it's multicultural and international, rather than only focusing on the Mexican situation. People ask us this: do we have evidence that that is really important? No, in actual fact, we don't. We don't know if euploidy is different in Japan than it is in the Philippines or different in South Africa. We do not know that. We do not have that information. But people keep asking us, and it's a valid question, because genetic populations, population genetics is extremely important, has been important for 100 years. So we will look at that, but so far we have no evidence that it really on a gamete level makes any difference. So this new system 2.0 is generalizable. It learns from its findings. The first one was limited in that respect. And the first one also needed clinic fine-tuning. We had to make different settings for each clinic. This one is plug and play. The new one is plug and play. It doesn't matter what your preferences are when you transfer embryos or what your ground truth is. This is a report. There are many different types of report and evaluation possibilities. It has a 79% accuracy rate. So in other words, don't use it as a genetic test. If it tells you it's normal or it is the highest ranking, don't think that means it's euploid. That we're not trying to say. It was tested on euploidy, because euploidy assessment is a direct assessment of the embryo. It's a direct assessment of Erica. Whereas if we look at pregnancy outcomes, that's an indirect assessment. It's not a KPI, it's a PI. And we really want to look at KPIs and train the database on KPIs. So that's why we chose PGTA, because in spite of all the discussion about it, there's little doubt that the PGTA assessments are very accurate and are directly coming from the embryo rather than pregnancy, which is affected by all sorts of other factors. So it is trained on ploidy outcomes, but we don't think we should not use it as a genetic test. So these embryos are also scored from 0 to 100. You'll find 100 very, very, very rarely. Over 90 would be a very good result. Everything over 80, everything over 75, we consider normal. So here you have on this report on the right, you see 2 green bars for embryo that was ranked A and embryo that was ranked B, 86 and 80, and we consider that as normal. And that is associated with the embryo that you see in the report. Here you see that in another way. And if we look at those embryos from different clinics and look at the scores and associated with euploidy outcomes, we see that there is clearly that the embryos are prioritized according to their euploidy. So in green in the middle you see euploidy, the yellow ones are in between in yellow, and then it's mosaicism in yellow, and aneuploidy, which is shown here in red, orange. And so you can see a big discrepancy, but it is significant, highly significant. But there is so much overlap between all those groups that from that particular graph you can see, don't use it as a genetic test. It just should be used as a ranking system. Here's another way of looking at this, but this was not done on real embryos, this was done on synthetic cycles, which are all randomized and actually beautifully composed, so it tells you a lot. And you can see here the green dots represent euploidy, the yellow one mosaicism, and the red, orange ones are aneuploid embryos. And you can see that the score on the vertical axis goes from 0 to 1, 0% to 100%. And you can see how it differentiates nicely and splits those embryos out very nicely with the yellow ones in the middle, the mosaic ones, or assumed mosaic ones in the middle. So how is AI changing embryo selection in clinical IVF? In conclusion, it improves confidence. The AI is an assistant. It gives you an opinion and it's solid, because it may change over time because more data is coming in, but it gives you that confidence that you may not always have when you do your ranking analysis. It will long-term, it will optimize, and you will learn from it. It's important to see what an AI thinks about an embryo, because maybe your own idea as an embryologist about that embryo or that embryo cohort is very different. And so you may learn what those differences could possibly be. Maybe you won't learn. That's a possibility too. But at least it's an interesting process when you use it. It may improve implantation, and at least we have seen that from the first version. The second version is so new that we don't have the feedback yet, and hopefully people will use it not only as a tool, but also as a way to do trials in their own clinic and share this as much as that is possible. And you get advice from multiple sources. You have 42 clinics so far feeding into this system. And so you add more, you're actually using the wisdom of the world community to actually help you doing a ranking selection. I think I mentioned this in the beginning. One of the objections that was made early, not just about AI in our field, but about AI in medicine in general, is you need to have transparency when you have a score, when you have a diagnostic test where you use AI. And often the methodologies are not transparent. And so here we disclose transparency in this particular slide, disclose transparency of these two AI applications. SID is transparent, or more transparent than the average AI in our field. The embryologist sees sperm ranking in real time with numbers, with reports. It will give you a score, and it will give you the way that sperm was recorded and how motile it was, what the motility parameters were. So, but that doesn't mean you have to use it, you can still ignore it. ERICA is less transparent. It has predictive power, but more black box qualities to it. The embryologist can also ignore this selection, of course. We'll work on getting ERICA to be more transparent and change the reporting functions so that the embryologist and the doctor can share in the development in why the AI decided on the ranking system it used. I'd like to thank you, of course. I'd like to thank the moderator and Kitazato and these collaborators here, listed here, for their contributions to this presentation. Kitazato and IVF 2.0 are now in a partnership for innovation. We have formed a strategic partnership, and our collaboration aims to improve innovation, to bring innovation to the forefront, and to provide new solutions to the art field. Thank you very much.